Okay, today what I'm going to do is show you how to work on an oral absorption problem given a data table that shows various time points and the corresponding plasma concentration of a drug. So in this example problem, what is shown is what it says is the dose that was given is 500 milligrams. It was given orally, and the plasma levels were determined at various time points, as shown there. In every hour after the dose was given, the plasma level was measured 1, 2, 3, 4, so all the way up to 10 hours. And the concentrations were determined and as shown on the table in micrograms per ml. And given this data, we can calculate two intercepts. Now, when we go through this problem, you'll realize that this is very similar to the two compartment model problem that we learned about earlier when discussing IV bolus two compartment model. However, this is one compartment oral dose model, okay? And we can also calculate, apart from the two intercepts A and B, we can calculate two rate constants, KEL and KA. KEL, is similar to beta that we calculated the in a two-compartment model. So these Greek letters can also be used to represent the rate constants. Beta for KEL and alpha for Ka, which was a absorption rate constant. So the method that we use for this is method of residuals. Now, one thing to note here in this data table is that if you were to create a graph, which I encourage you to create a graph on Excel using the data that is given in the sample problem. So if this is time and this is concentration, you'll see that the concentration would increase up to a certain point and then decrease. So the tip of that peak is Cmax. I mentioned that during my lecture that I posted earlier yesterday. Is Cmax, and the time point here corresponding to Cmax is Tmax, the time it took to reach Cmax. Now, at this point, at Cmax, at Tmax, absorption is complete. So that is something that is similar to distribution being complete in the two-compartment IV bolus model. Here we say absorption is complete, and so clearly we have to delineate between two parts in this graph while doing the math. The elimination can be calculated from the terminal phase after absorption is complete, and the absorption rate constant or the absorption part of the process can be calculated from the first part of the graph. And so we have to delineate, we have to separate these two parts of the data. So if you look at the data, 1 hour the concentration is 3.13. An hour later, 2 hours, 4.93, and 3 hours, 5.86, 4 hours, 6.25, 5 hours, 6.28, and then 6.11, then 5.81. Do you see what was happening there? The plasma level increased as the absorption proceeded, and when the absorption stopped, no more rise, but rather a fall in concentration. So let's say for this problem that the absorption was completed after 4 hours. Okay, let's say absorption completed after 4 hours. So what that means is we have to use time point 5 hours and later for calculating the elimination rate constant. So 5 hours, so we have to use linear regression. We have to use linear regression and we are going to determine B and KEL. So when you use linear regression in your calculator, you have to get to the statistics mode, clear all the data that is already there, and then for time, you will use 5 hours, and for concentration, you would use natural log of 6.28. So natural log of 6.28, and so on. So for 6 hours, natural log of 6.11. For 7 hours, natural log of 5.81. For 8 hours, natural log of 5.45, and so on up till 10. Okay, natural log of 4.66. So we got to go use your calculator in statistics mode. So I'm already in statistics mode. I'm actually entering the data, x1 as 5, y1 as natural log of 6.26, x2 is 6, y2 is natural log of 6.11, x3 is 7, y3 is natural log of 5.81, x4 is 8, y4 is natural log of 5.45, x5 is 9, y5 is natural log of 5.06, and x6 is 10, y6 is natural log of 4.66, and you click state there and you scroll all the way and you get to highlight A, which is actually the slope, which is actually KEL, 0.06 per hour, 0.060 per hour. And then you scroll one more, you'll get B, which is the intercept, and to calculate the intercept uppercase B, you have to do e raised to B, which is e raised to 2.161, and you get that as 2.161, 8 point, I'm going to round it to one decimal place, it's 8.7 micrograms per ml. Okay, so we are found KEL as 0.060 per hour and B as 8.7 micrograms per ml. That's one part of the problem. Now we know that the next part of the problem is to use the method of residuals, right? to use the method of residuals to calculate the rest of the parameters that are being asked there. So to do that, the method of residuals, we know, starts off by calculating the extrapolated concentration. So here, when we talk about extrapolated concentrations, what we are actually referring to is we have this part of the graph and we have the first part of the graph, and then we can actually extrapolate the elimination part of the graph all the way to y-axis that way. So the plasma levels corresponding to the first 4 time points, 1, 2, 3, 4, that lie on this part of the graph, the extrapolated line. That is the extrapolated values. So in order to calculate that, we know we need the equation that we just calculated, the equation that we just determined. So the equation for the straight line, this is the straight line that I'm referring to, is C is equal to 8.7 micrograms per ml times e raised to negative 0.06 times t. And all you have to do to calculate extrapolated values is to plug in the first 4 time points in that equation. 8.7 times e raised to negative 0.06 times 1. The second extrapolated is 8.7 times e raised to negative 0.06 times 2. The third is 8.7 times e raised to negative 0.06 times 3. And the fourth and final extrapolated value is 8.7 times 8.7 times e raised to 0.06 times 4. And you can calculate that using your calculator. Again, remember to clear the data and enter the data starting with x1 is 1. Before that I need to do the calculation, right? I need to do the calculation, the math. 8.7 times e raised to negative 0.06 times 1 is, I'm going to round it to 1 decimal place, or 2 decimal place, because actually in the data we have 2 decimal places. 8.19 is the first extrapolated value. 8.7 times second e raised to 0.06 times 2 is 9.81 is the second extrapolated value. I made a mistake while doing the math. Sorry, this second value is not 9.81. It is, I made a mistake. It is 7.72. The third value is 8.7 times second e raised to negative 0.06 times 3, which is 7.27. The last extrapolated value is 8.7 times second e raised to negative 0.06 times 4 is 6.84. So these are all in micrograms per ml, and these are the extrapolated values. Okay, these are the extrapolated values. The next step is to calculate the residual concentrations. And to do that, I need to do something here. So we need to calculate the residual values in the next step. So residual values. That is by taking the first extrapolated 8.19 and subtracting the first value in the table, 3.13. Similarly, the second extrapolated value, 7.72 minus 4.93. Then the third extrapolated value, 7.27 minus 5.86. And the last extrapolated value, which is 6.84 minus 6.25. So we get the residuals that way. This is kind of very similar to what we did with the two-compartment model. We take one value and subtract the other. You have to choose the values properly without making any mistakes so that you don't run into problems or issues when you do the calculation. Got to be very careful when you do this, or you can easily run into problems. 2.79 is a second residual. 7.27 minus 5.86 is 1.41. 6.84 minus 6.25 is going to be equal to 0.59. And now to calculate Ka or alpha, what we need to do is to calculate A and Ka or alpha, all you have to do is use linear regression and for x you will be time and y is equal to natural log of 5.06. So then again the next x2 is 2, y2 is natural log of 2.79 and so on and so forth till you complete. So I can write that down explicitly. Let me write that down, all of those down, so that you will know. So x1 is 1 hour, y1 is natural log of 5.06, x3 is 3, y3 is natural log of 1.41, and x4 is equal to 4, and y4 is equal to natural log of 0.59. So you have to do that in your calculator in the statistics mode. Got to remember to clear data, enter the data. X1 is 1, y1 is natural log of 5.06, x2 is 2, y2 is natural log of 2.79, x3 is 3, y3 is natural log of 1.41, and x4 is 4, y4 is natural log of 0.59, and you click stat var and you'll get the values that you're looking for. You just keep scrolling until you highlight A, which is your alpha or Ka, or the slope, which is 0.712 per hour if I use 3 decimal points. then you get B as 2.398, but you know that the intercept is calculated by e raised to 2.398, which is 11 microgram per hour. So what we actually did just now was we actually generated the graph, although we did not actually draw the graph. We drew the graph like that. We extrapolated the graph to there. We determined residual values and then drew a straight line through those residual values. Pretty similar to what we did with the two compartment model problem there, right? So we have determined the A, KA, and B, and KEL. And now you can go back and use the general model. C sub t is equal to B e raised to negative beta t minus A times e raised to negative Ka or alpha t. Either one is fine. You can do that. Minus alpha t. It's the same as b e raised to negative K EL times t minus A e raised to negative Ka times t. So either one should work. So that is the method that you can use to calculate these values. And now that general equation can be used if the bioavailability of the oral drug is 1. This equation can be used to predict what the plasma level will be, say, 12 hours after that 500 milligram dose was given. We have data in the table given up to 10 hours, right? We can predict what is the plasma levels 11 hours after the dose, 12 hours after the dose, 15 hours after the dose, and so on, using this equation, provided the bioavailability is equal to 1. I now encourage you to go back and work on this problem on your own, step by step, just the same way I did, and then determine the values that are being asked there in that problem. And I have put up a few top hat questions on those. Enter those values after you have done the math yourself. Please go ahead and do this yourself, otherwise you will not be able to approach this problem if you're asked to do this in an exam. Please go ahead and do this and enter the values on top hat. Thank you for your attention.